This analysis will cover an architectural methodology for achieving system coherence. It's intended to present a structural alternative to the more conventional control-centric models. The focus here is on interaction patterns rather than component-level states as the primary determinant of a system's stability. The discussion is structured into 6 parts. First, we'll examine the fragility inherent in control-centric models. Second, a formal definition of structural coercion will be provided. Third, we'll look at a discipline for non-interventional observation. Fourth, the specifics of a reflective loop architecture. Fifth, the roles of temporal slack and relational alignment. And finally, Section 6 will cover the resulting implication for governance. So, Section 1. This part examines the foundational problem with many contemporary system models, which is an over-reliance on optimizing individual components. The core issue can really be framed as a contrast between 2 distinct architectural postures. On one hand, there's the node-centric view. This assumes that if individual components are stable, then the entire system will naturally be coherent. On the other hand, a relational architecture defines coherence quite differently, as a property that emerges from the structure of the interactions between those components, not from the components themselves. The node-centric model then makes a kind of categorical error. By locating coherence within individual nodes, it effectively obscures the role of the interaction structure. What can happen is that excessive local stabilization actually creates a relational rigidity, and this ends up undermining the adaptive capacity and the coherence of the whole system. Moving to Section 2, here we'll formally define the mechanism that produces this fragility. It's a concept called structural coercion, or forcing. Forcing is defined as a structural property of an interaction loop. It isn't a moral or a psychological phenomenon. It is simply any architecture where system progression depends on imposed action or constrained choice. This has the effect of collapsing interaction into a mechanism of control. Now, this architectural choice has 3 direct structural consequences. First, it reduces observability because it becomes impossible to distinguish a genuine state change from mere compliance. Second, it increases hidden load by displacing the adaptive effort to areas outside of the formal system. And third, it makes the system brittle, accelerating boundary breaches by reducing its tolerance for any variance. The alternative posture, then, must begin with a disciplined approach to observation, one that avoids introducing the very forcing it seeks to understand. The first condition for this is longitudinal exposure. This isn't about data saturation, it's about temporal openness. This condition renders coherence observable through its persistence over time. Duration, in this posture, matters more than intensity because it allows patterns to reveal themselves through continuity rather than simple reaction. The second condition is structural admissibility. This acts as a precondition for the observation itself, a gate that ensures the integrity of the observational setup. An observation is considered admissible only if the system is not being forced towards stabilization or optimization. Any such intervention would invalidate the observation. And the third condition is indexing without scoring. This is a practice of structural notation, not one of measurement. It simply marks the presence or absence of persistence, of coherence, without assigning any value, rank, or direction. It only records that persistence was or was not observed. This brings us to the second major component of the alternative, an interaction architecture that can operate without coercion. Reflective loops are distinct from reactive or directive systems. They function as a mechanism to maintain alignment between a system's state and its response, but critically, without imposing a direction. Input here is not a command to be executed, but rather a signal to be integrated. A reflective loop is structured as a 4-stage cycle. Stage 1 treats input as an undifferentiated signal. Stage 2 involves selective attention, but without resolving the input. Stage 3 provides descriptive feedback, reflecting how the input was registered, not how it should change. And the final stage produces a stabilized output, which means the loop closes without any obligation to escalate. In this section, we'll examine how these architectural components allow for the emergence of genuine system stability. Reflective loops introduce a critical property, temporal slack. By decoupling input from any immediate enforced output, they allow the system's response to be modulated through pacing and optionality. This structural property accommodates variance in system capacity and prevents escalatory dynamics from taking hold.
This slack enables what can be termed relational alignment. Now, this is not the same as synchrony or consensus. It is the capacity of interacting nodes to remain mutually compatible over time. Alignment is maintained through ongoing modulation, not through convergence to a single uniform state. And this property is what constitutes coherence. The final section will synthesize these concepts to address the direct implication of this methodology for system governance.
This quote illustrates the central conclusion. The objective is not to direct the system toward a preset goal. Instead, stability is an emergent property of an interaction environment that is designed to be non-coercive, allowing adaptive alignment to occur without being forced. Therefore, the primary governance implication is an architectural reorientation. Priority must shift away from optimizing the efficiency of individual components and toward ensuring the relational compatibility of the interaction architecture. System integrity, it turns out, resides not within the nodes, but in the structure of their interaction.